China just handed us something extraordinary. While NASA sat on 43 days of silence, a spacecraft orbiting Mars quietly achieved what Earth-based telescopes never could. Measuring the trajectory of 3I Atlas, our newest interstellar visitor, with 10 times the accuracy previously possible. 10 times, not a modest improvement, a revolution in precision. The Tianwen-1 Mars orbiter, equipped with imaging instruments far more stable and sunlight-isolated than anything we have on Earth, has mapped this object's path with such clarity that we can now read its story in unprecedented detail, where it came from, how forces are acting on it, and most critically, whether it behaves like a natural comet or something else entirely. According to Harvard astrophysicist Avi Loeb, this measurement changes everything, because in interstellar science, trajectory is biography, and 3I Atlas just revealed something we cannot explain. For years, astronomers struggled with a fundamental limitation. Earth is a terrible platform for tracking interstellar objects. Our atmosphere distorts light. Our planet's orbital motion introduces noise. Ground-based telescopes see a wobble where precision is needed. Even Hubble, positioned above the atmosphere, still orbits Earth and shares our perspective, our blind spots. Mars changes the geometry entirely. Tianwen-1 orbits the red planet at a vantage point that is stable, shadow-isolated, and critically positioned for parallax measurements. Where Earth sees atmospheric turbulence, Mars sees a clean line. Where ground observatories wrestle with Earth's own motion through space, Tianwen-1 maintains a fixed baseline millions of kilometers away. The result is observational clarity that Earth-based platforms simply cannot match. This is not a minor technical upgrade. This is a paradigm shift in how we study fast-moving objects from other stars. With 10 times better positional accuracy, scientists can now measure non-gravitational accelerations with confidence, distinguish between natural outgassing and anomalous forces, and predict trajectories months further into the future than before. Loeb has long argued for multi-planet observational networks precisely for this reason. A single viewpoint limits understanding. 2 viewpoints reveal depth. 3 or more create a triangulation powerful enough to decode the physics of objects moving at tens of kilometers per second through our cosmic neighborhood. Tianwen-1 just proved him right. The spacecraft has given us a second eye, a Martian perspective that transforms 3I Atlas from a blurry mystery into a readable text, and what that text reveals is deeply unsettling. Here is what the refined measurements show. 3I Atlas is experiencing non-gravitational acceleration that does not fit the standard equations used for natural comets. Let that sink in. This is not speculation. This is measured data from a Mars orbiter with unprecedented precision. The comet is deviating from its gravitational path in ways that surprise even veteran astrophysicists. Natural comets deviate too. Solar radiation heats ice on their surface, causing jets of gas that push them gently off course. We have models for this. We have equations. The deviations are predictable, chaotic, fluctuating as patches of ice heat unevenly across a rotating nucleus. But 3I Atlas shows something different. The acceleration is smooth, continuous, almost steady. When plotted against time, the force acting on 3I Atlas does not behave like random outgassing. It behaves like a persistent directional push, as if the source of acceleration is stable rather than sporadic. Natural outgassing is messy. This is not messy. This is elegant. 3 possibilities emerge, and none of them are comfortable. First, the conservative explanation. 3I Atlas contains deep reservoirs of hypervolatiles, exotic ices that vent in unusually stable patterns. Possible, but unprecedented. We have never observed such behavior in any comet, local or interstellar. Second, the speculative explanation. This object is composed of unfamiliar interstellar materials whose thermal response differs fundamentally from anything formed in our solar system. Materials that sublimate at distances where ordinary ice should remain frozen. Materials that produce thrust with an efficiency we have never modeled. Third, the explanation Loeb has been warning us about since Oumuamua. We are witnessing an object experiencing radiation pressure in a manner consistent with a thin, light sail-like geometry. Not a solid rock, not a fluffy comet, something engineered. Before Tianwen-1, skeptics could dismiss these anomalies as observational noise, Earth-based measurement error, atmospheric distortion. Not anymore. Mars does not have Earth's excuses. The data is clean, the acceleration is real, and the smoothness of that acceleration is the signature of something we do not yet understand. Loeb has calculated the odds before. With Oumuamua, the probability of its trajectory and acceleration profile arising naturally was 1 in 100 million. Now 3I Atlas arrives with its own set of improbable behaviors, measured with 10 times the accuracy, and the pattern holds. This is not belief. This is mathematics, and the mathematics are screaming at us to pay attention. The Galileo project, led by Loeb at Harvard, is now preparing to examine 3I Atlas for potential technosignatures. Not because scientists want to find alien probes, but because the evidence, the trajectory, the non-gravitational forces demand investigation. In science, when something does not fit the model, you do not ignore it. You build a better model, or you admit the model was incomplete all along. This Mars-based measurement is not just academic. It has immediate implications for planetary defense and cosmic evolution. For most of human history, we assumed the greatest threats to Earth came from local asteroids, fragments from our solar system's formation. But the appearance of 3 confirmed interstellar objects in less than a decade forces a recalculation. If interstellar debris is more common than previously believed, then our planetary defense models must adapt quickly. Why? Because interstellar objects move faster, much faster. Typical asteroids travel at 15 to 20 kilometers per second relative to Earth. Interstellar visitors like 3I Atlas arrive at 30, 40, even 50 kilometers per second. That velocity difference translates to drastically shorter warning times. If even one interstellar fragment were on a collision course, detection and response windows would collapse. This is where multi-planet observational baselines become essential. Earth sees one angle, Mars sees another. Future missions around Venus or Jupiter could provide even more perspectives. With 3 or more observation points distributed across the solar system, we can triangulate interstellar objects months sooner than before, calculate their trajectories with tenfold precision, and predict threats long before they become emergencies. Tianwen-1 has just demonstrated proof of concept. A spacecraft orbiting Mars, working in coordination with Earth-based telescopes, has achieved what neither could accomplish alone. This is the architecture for a solar system-wide early warning network. Not science fiction, not distant future planning. This is happening now. The Tianwen-1 data is only the beginning. Over the next few months, NASA and the European Space Agency will refine their orbital models using the Mars measurements as a new baseline. Ground-based observatories will attempt to detect microfilaments and structural variations in 3I Atlas as it approaches perihelion. Radar arrays will search for metallic content, looking for reflectivity signatures inconsistent with pure ice and rock. The Galileo project under Loeb's direction will deploy advanced imaging systems to examine the comet for potential technosignatures, geometric patterns, surface reflectivity anomalies, electromagnetic emissions. These are not fringe investigations. These are legitimate scientific inquiries driven by legitimate anomalies in the data. Planetary defense networks will incorporate new algorithms trained specifically on interstellar behavior, accounting for the higher velocities, unpredictable chemical compositions, and non-gravitational forces that distinguish visitors from other stars. This is the dawn of interstellar astronomy as a practical discipline. For decades, studying objects from other solar systems was theoretical, limited to spectroscopy and distant observation. Now, with multi-planet coordination and unprecedented measurement accuracy, we can analyze these travelers in real time, extracting information that rewrites our understanding of cosmic evolution and galactic debris fields. 3I Atlas will not remain visible forever, but its trajectory, measured from Mars, will endure as a blueprint. China's Tianwen-1 has given us more than Precise measurements. It has given us proof that humanity can function as a multi-planet civilization when necessary. Loeb has argued for years that trajectory is biography, that the path an object takes through space reveals its nature. Tianwen-1 proved him right. The Mars orbiter read 3I Atlas like a text, decoding non-gravitational forces with 10 times Earth's accuracy, and revealed anomalies that demand explanation. Whether those explanations are exotic ices, unknown materials, or something far stranger, one truth emerges clearly. We are not alone in tracking the skies anymore. Earth and Mars are watching together. And that cooperation, that quiet, profound act of multi-planet coordination, is humanity's first real step toward becoming a species that listens to the galaxy. Stay curious. Stay vigilant. The universe sent us a visitor. Thanks to Mars, we were ready to receive it.